Welcome to the new era of video creation with Bayozi 8. Today, we will discuss what is the vanishing gradient problem. What is the vanishing gradient problem, and how can you mitigate it when training deep neural networks? The vanishing gradient problem is a challenge in training deep neural networks, especially when the network has many layers. It refers to the issue where the gradients of the loss function with respect to the network's weights become exceedingly small as they are propagated backward through the layers. As a result, weights in the earlier layers stop updating significantly, causing the model to learn very slowly or even halt entirely. This issue is most pronounced in deep neural networks, DNNs, with many hidden layers, especially when using certain activation functions, like the sigmoid or TNH. The gradients in these networks become very small as they are propagated from the output layer to the input layer, which leads to slow or no learning. It's an important issue to address because it can greatly affect the ability to train deeper models efficiently. The vanishing gradient problem often occurs due to the nature of certain activation functions. For example, sigmoid and TANH functions squash the output values to a small range, 0 to 1 for sigmoid and 1 to 1 for TANH. When you compute the gradients for backpropagation, the derivative of these functions becomes very small, leading to a shrinking gradient during each step of backpropagation. The backpropagation process involves propagating gradients backward through the layers of the neural network to update the weights. As the gradients pass through each layer, they are multiplied by the derivative of the activation function. If this derivative is very small, the gradient shrinks exponentially as it moves backward. The chain rule used in backpropagation amplifies this effect, causing the gradients to diminish more and more as they propagate through the network. This is particularly problematic in deep networks with many layers, where the gradients can effectively vanish by the time they reach the earlier layers. The vanishing gradient problem severely hampers the training process, especially for deep neural networks with many layers. When the gradients vanish, the model's learning process is slowed significantly or may stall altogether. This means the model takes much longer to converge, if it converges at all. Without substantial gradients to guide updates, the training process becomes inefficient and slow. Stagnation in the weights occurs, as earlier layers may fail to adjust their weights effectively due to small gradient values. This freezes parts of the network, preventing the model from improving. The optimization process is also hindered, since the gradient updates for the parameters in the earlier layers become insignificant, meaning the model cannot effectively update these weights. This limits the ability to train deeper models, making it difficult to scale neural networks to handle more complex tasks. One of the most effective ways to mitigate the vanishing gradient problem is by using ReLU, rectified linear unit, as the activation function instead of sigmoid or TNH. ReLU is defined as fx, max, 0, x, fx, 0, max, 0, x, which means it outputs the input if it's positive and 0 otherwise. This is a non-saturating activation function that allows the gradients to flow through the network without shrinking. Since ReLU does not squash the input into a small range, it helps prevent the gradients from becoming too small during backpropagation. The gradient propagation through ReLU remains constant for positive inputs, allowing for efficient gradient updates. This mitigates the vanishing gradient problem and allows the network to learn faster. However, ReLU can sometimes suffer from the exploding gradient problem if the gradient values grow too large. While this is an issue, techniques like gradient clipping can help manage it. Batch normalization, BN, is another technique that helps alleviate the vanishing gradient problem. It normalizes the output of each layer during training, ensuring that the activations have a mean of 0 and a standard deviation of 1. By doing so, BN stabilizes the distribution of activations across layers. The normalization of activations prevents the gradients from shrinking excessively during backpropagation. This helps maintain consistent gradient magnitudes throughout the network. Batch normalization ensures that the gradients don't vanish as they propagate through the layers, improving the stability of the training process. By stabilizing the activations, BN allows the use of higher learning rates and can accelerate convergence. This is particularly helpful for very deep networks. However, batch normalization requires additional computation and can introduce some overhead in terms of training time. Xavier initialization is a weight initialization strategy that helps mitigate the vanishing gradient problem by setting the initial weights of the network appropriately. It scales the weights based on the number of input and output neurons to ensure that the activations do not explode or vanish during the initial forward pass. By adjusting the weights in this manner, the variance of the activations and gradients is controlled. This leads to a more balanced flow of gradients, preventing them from either vanishing or exploding. The scaling factor used in Xavier initialization ensures that the weights are not too large or too small at the beginning of training. Proper initialization is crucial for deep networks, as it ensures that the model starts off with a good starting point for learning, leading to better convergence and preventing early-stage issues like vanishing gradients. Skip connections, or residual connections, are another powerful technique to combat the vanishing gradient problem. They allow the gradients to bypass certain layers by directly connecting a layer's output to a deeper layer. This concept is widely used in residual networks, ResNets, which are designed to handle very deep networks. Skip connections provide an alternative path for the gradients to flow, preventing them from shrinking too much through multiple layers. By creating these residual connections, the model can learn identity mappings that help preserve gradients, allowing for faster convergence even in very deep networks. These connections enable the training of networks with hundreds or even thousands of layers, making them highly effective in tasks requiring deep feature extraction. In addition to the aforementioned techniques, there are other approaches to manage the vanishing gradient problem: gradient clipping. This technique involves limiting the magnitude of the gradients to prevent the exploding gradient problem, which is the opposite of vanishing gradients but still an important concern. Leaky ReLU, a variant of the ReLU function that allows a small, non-zero gradient for negative inputs, avoiding the dead neuron problem where neurons stop updating. LSTMs. For sequence modeling tasks, long short-term memory, LSTM. Networks are designed to combat vanishing gradients in recurrent neural networks by using gating mechanisms to preserve long-term dependencies. Optimizers like Atom and RMS-Prop can also adaptively adjust the learning rate, which helps the network avoid vanishing or exploding gradients. In conclusion, the vanishing gradient problem is a key challenge in deep learning, but several techniques can mitigate its impact. These techniques are crucial for ensuring that deep models can be trained effectively and converge more quickly. ReLU and its variants provide a non-saturating activation function that allows gradients to propagate more easily. Batch normalization normalizes activations, ensuring stable learning. Xavier initialization and skip connections set up better foundations for training deep networks. Finally, strategies like gradient clipping and LSTMs offer further solutions for training robust and efficient neural networks. By understanding and applying these techniques, deep neural networks can be trained on larger and more complex data sets with much better results. To successfully train deep neural networks, addressing the vanishing gradient problem is essential. While there is no one-size-fits-all solution, using a combination of techniques tailored to your model and task can lead to optimal results. Experimentation is crucial. Each model and data set might require a different approach or combination of techniques. Recent advancements in deep learning continue to improve methods for training very deep networks, so staying updated with new research is important for optimizing training.